Hey guys, welcome to day 87 of Codeforces Everyday until GM. Still a little bit sick, my throat might be a little bit raspy, feeling a little bit better, but we're gonna get a video in. Just woke up, couldn't fall back to sleep, so that's why I'm recording it for in the morning, but uh, let's get something done. I was looking at this problem last night, and it's been stuck in my head for a night now, so let's just go ahead and do this problem. So what's going on is we're given this snowflake graph. The graph is generated from two integers x and y, both greater than 1. We start with one central vertex. X vertices connect to the central vertex, and then each of the branches have y vertices connected to each of them, sort of like this. So this would be x would be equal to 5 because 5 things are connected to it, and then for each of these nodes here would be our y, and they have 3 things connected to it, not including the one connected to the center one. And so I was laying in bed and I was thinking about this problem, and I think I finally got a solution that might work, which is why I'm recording this now. Originally, what I was trying last night was just counting however many, counting each of the connections, and but this didn't really work out. As I was trying some things, this didn't really work out because it runs into some problems of problem one. If you just count the vertices, that will only work specifically for cases that you allow it to work, and so it's kind of hard to enjoy without drawing a ton of stuff. So I'm just gonna draw out some contradictory cases. There's case one where you have your 1, and then you have your, say, 2, 3. There's this sort of case where x is 2, y is 1, or y is 0. So this is case 1, and this is kind of standard. Y can't even be 0, I don't think. Y, let me see. 2 integers, the numbers. Yeah, it has to be. Well, can y be 0? Not totally sure, but okay, there's this kind of case. There's also kind of case where it's oh my god, 1, 2, 3, 4, 5, where it's 2, 1, and then just originally what I thought I could do was just count the connection, and pick between how often they show up, right? So for example, if I had a connection of, I don't even know why I drew these examples. I thought I was onto something, but these don't actually counter what my original thinking was at all. Okay, let's just go back to this thing. If I had this thing, I thought I could just count, oh, this 5 connection shows up 1 time, so that will be our x. And then each of these will have a 4 connection, so it's just 4 minus 1. But what I'm trying to say is that runs into issues when each of them have a 5 connection. So I guess the easiest case would be 2, 3. I guess this would be the easiest case. That's why I drew it. Where each of these have, this is a 2 connection, but technically for each of these nodes it's a 2 connection too. We just process the -1 at the end, right? Which becomes an issue because then you don't know which one is the center node. Or I guess if you find everything is equal, you can probably just print like max, because what this means, like what the idea of printing max is, max comes from is that you'll always have one connections, because these edge nodes will always have one connection to the center node. It's similarly, these will have one connection to their parent node, right? But then everything else will have two connections. So you have like um, three two connections, and then two connections, three two connections, and then two one connections. And so my original thinking was, you can just pick this to be x, and then um, like for example, if you had a case where you had, I guess this case would be perfect, one 5 connection and 4 and 1 2 3 4 5 and 5 4 connections, and then you would have 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 1 connections. Then we can just choose, something's not right here. This should be a 4 connection. We should have 5 4 connections. So then we would just choose the one connection to be our x, and then our second greatest to be our y. And then, but then you run into a scenario where you can have like, wait, is this still possible? Now I'm doubting whether my original thinking was wrong or not. This sucks. Okay, so we have, this is a 2 connection, 1 2 connection. We have 1 2 3 4, 2 4 connections, and then 1 2 3 4 5 6 1 connections. So you will never choose the 1 connections. You can just ignore these. You would look at the 2 different ones. And then you would pick the top one. Or you'd pick the 1 connection to be x. This would be x. And then this would be y. I guess these are our 3 cases, no? Wait, did I just crack it? Maybe I wasn't... This was kind of my original thinking, but I guess I didn't go in depth enough. Wait, let's double check this. So, sometimes we will have cases where, well, we always have a case where we only have one. Well, unless it's this, we should have a number with 1 1, right? We could have like something like this. Does this change anything? We would have a 3 connection, 3 2 2 connections, and then 3 1 connections. So we'd look at these two, and then our 1 connection would be 3, and then our 2 connection would be 2, or our 2 connection would be 2 months. Wait, Loki, this might be the answer. Ah, Why did I just gloss over this yesterday? Loki, I think this is right. And if everything's the same, we just print two minus 1. We print max minus 1. Right? So we will always have max. We'll always have 1 connections. This should be number of connections. Our dictionary should be number of connections, or our, yeah, number of connections. Count of connections. So basically, the number of connections and then the number of nodes with this number of connections. So we can just call this like count of node count. Something like this. Okay. So what we can do is, so we're getting all the edges in an array first. What we can do is use a counter. Collections import counter, and then edge counter equals counter edges, print edge counter. What this should do is, okay, this is working out this case, right? 15 has 5 connections, 20 has 4 connections. Okay, we don't actually care about the actual number, right? We only care about the connections. Because what our final output is the number of connections of X, number of connections of our center, and number of connections of each of the center's children, right? So we don't actually care about this value. We only care about the values. So we do top 2 is equal to edge counter of values count of values set. Sorted set reverse equals true. This won't work. We need a special for our edge case, right? Top 2 should, okay, this should take 5 4. Yes. But this won't work for our other case if I just bang it out real quick. 1, we will have this is number of Is this what I want? Have I already played with this? 1, 2, 1, 4, 2, 3, 4. Yeah, okay, this is it. This is the case I'm looking for. The top 2 is 2, 1? Why is it 2, 1? A 1 counter is 2. We don't want a 1 counter at all. Our 2 counter is 2. Wait, what? Oh, this is the number of times it shows up, which is, okay, 1 is 2, 2 is 2, 4 is 2, 3 is 1, 5 is 1, okay. Okay, so when this is there ever a case where it's this? It's vertices, edges, right? 1. Okay. So I think this might be a special case that we take care of. And this would be 2, 0. Or this would be 1, 0. If len top 2 is equal to 1, print 1, 0. Continue. Otherwise, if 1 is in our top 2, that means we have a situation like this. Well, what if it's simply just 2, 3, like this? Then this would be three nodes, 2 edges, 1, 2, 1, 3. It'd also be 2, 1. So these would be the same, but they don't give the same answers, right? Because this would give 2, 1. This would give 2, 0. Okay. Value counter. Equals counter edge counter dot values. Top 2. Then value counter should count the top two values. Okay, let's not worry about these edge cases for now. We'll worry about them later. Let's see if we can make it work for everything else first. So, assuming we grab a top two. Okay, wait, no. Let's consider if these cases break other situations. This might be the exact reason why I thought this wouldn't work the last time I looked at this problem. Top two. We're gonna need a value counter anyway, right? Why do we have the... Why don't we jump straight to the value counter again? Is it specifically for these edge cases? It might be. Okay, we're gonna need a value counter anyway, I think. Value counter edge counter dot values. Print value counter. Let's print it all at the end so I don't get confused. Counter. Okay, this is correct. Okay, I should put in this case. 1, 3, our number of nodes 1, 2, 3, 4, 5, 6, 7. Edges is 1, 2, 3, 4, 5, 6. We have 1, 2, 2, 3, 1, 4, 4, 5, 1, 6, 6, 7. Right. So 1 is connected to 3, 2 is connected to 2. Yeah, this is correct. And then our value counter. 3 is connected to 1, so this is our root. Hmm. 2, 1, 3. 2 is connected to 1, so this is our root. One, 0. Okay. This might actually be getting somewhere. So is it this? This. This. Okay. I think this is one. And then other one should be. Okay, so what this is doing is it's listing it by. It's basically sorting it by most common, right? So if I were to take out all these, it's sorting the value counter by most common. So 3 is most common, so this one goes first, and then this one, and then this one. Although I don't really know which order, but I know for sure that 1 is always going to be at the end, and there is always going to be 1 with 1 unless we run into a weird case of. I think this is the only case actually. Well, is this the case? No, because this 2 is 1. Then our 1 is 1. Is this a possible case? I guess it is, but then like how do you even distinguish what X and Y are? Because it feels like this could be X, but this also could be X. This could be 1, 1. This could also be 2, 0. So I need to figure out if zeros are allowed or not right now. It is guaranteed that this graph is a snowflake graph for some where both x and y are greater than 1. So this case is not even valid. This case we don't even have to worry about. Or both x and y are greater than 1. So this case we don't have to worry about. Okay, wait, this makes it so much easier. We don't have to worry about this case, we don't have to worry about this case either. So our worst case is this. Which I'm pretty sure is one of these. Is it this test case? 1, 2, 1, 3, 2, 4, 2, 5, 6, 7. Yeah. let's isolate this test case, I guess. And then we want to grab our last. So this is our x. So it's most common to grab the last one. We do this, and to grab the 2 here, we do 0. So this is just our x, and then our y should be the next greatest occurrence minus 1. So just this. We just don't need any of this. Maybe? Wow. Wow, I was just giga overthinking this. Okay, well, let's clean this up at least a little bit. Okay, so this is our smallest case, right? If x and y has to be at least greater than 1. So, which means 2 or greater. Or worst case is 2, 2. So, does it work for this case, which should be this one? Getting 2, 2. That's not right. Is this the right case? 1, 2, 1. That's this case. 1, 2, 1, 3, 2, 4, 5, 6, 7. So, okay, this is 2, 2. Where's my other one? 1, 2, 2, 3, 1, 4, 4. Okay, it's this one. They should give us 3, 1. Oh, this isn't even valid. Like, these need at least 2, right? Like this. So this isn't even a valid graph. This would need to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 9, right? And then it'd be 1, 2, 2, 3, 2, 4, 5, 6, or 1, 6, 1, 5, 5, 6, 5, 7, and then 1, 8, 8, 9, 9, 10. 2, 2, that's not right. Should be 3. Oh, I guess they all have 3 connections. So in this case, it'd be. Oh, that's not good. Wait, hold on. Glad we caught this case. One five three three two two. Okay, let's actually draw this out. One, take this case kind of seriously. 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So one connection, or was edge counter. One connects to 3, 2 connects to 3. So it becomes one connection, 3 connections is 3, and 2 connections. What is this? 2 connections. 9 is connected to 2. 9 is connected to 1, bro. How am I getting this? Fucking up. That's how I'm getting it. 1, 2, 2, 3, 2, 4. 1, 5, 5, 6, 5, 7. 1, 8, 8, 9, 8, 10. That's how I'm getting it. 3, 0 is not correct either. So if this is not equal to 1, we do something else. What do? We do this one twice. Three, 3. This is correct. This one failed. Why? It needs to be this. There you go. I think that's it. Let's submit it and sorry guys. Let's submit it and see. Wrong answer. Too good to be true. It seems like the right track though, no? I want to know if it's an edge case issue or if it's just... Alright, test 66. So there must be some edge case that I'm failing on. I don't even think this gets 66 inputs. Right. Yeah, no. In 30s. Like 25 or so. 25 to 30. So in some inputs, expected 4, found 5. Expected 4, found 5. $66 case. How would we get 4, found 5 if we had... I mean, the only thing I can think of is if it's four, and then these have five prongs. Hmm. Expected four, found five. It's something like some BS like this, or something like this. Or what it could be is another four. 1, 2, 3, 4. Case. I wonder how this would work for like a 4-4. Gosh, it's so much work. Okay, so whenever we have one of these where the edges are the same, or like where it's like the counts of y are the same as x, we only get two numbers. We only get two groups, right? Otherwise, we get three groups. So what we should do is Okay, this isn't 3, 3. This is 3, 2. Because we don't count this. This would be 3, 3. Which would give us 3 distinct numbers again. This needs to be -1. Is that it? I think that's it. Let's get rid of this print statement again and fix this to be 3, 2. I think that's it. Like, I would love to like handwrite another test case to confirm. It's just it takes so long. You have to draw so many nodes. So let's just run it and see. And it worked. Okay, that's all it was. Wow. Oh, that is a fun question. I'm not gonna lie. Okay. Let's see. I know I have some whips in here that we can maybe like knock out. Training before Olympiad. Okay, Masha and Alia have an important team Olympiad coming up soon. In honor of this, Masha, for warm-up, suggested playing a game with Alia. There's an array A of size in. Masha goes first, and the players take turns. Each move is described by the following sequence of actions. If the size of the array is 1, game ends. Okay, so it looks like they're going to be shrinking an array, right? Player who is currently playing chooses 2 different indices and performs the following operation. Removes AIAJ, okay, and adds to the array a number equal to AI plus AJ divided by 2 floor times 2. The first divides the sum of the numbers by 2, rounding down. Okay, yeah. Maximize the final, minimize it. Alright. Non-empty prefix. Okay. So we're not trying to figure out who wins. We just want the kth of these numbers should be equal to the number that will remain at the end with optimal play. Yeah. Okay. I need an example. 31. Okay, third test case. For prefix of length 1, the answer is 3. And 2, Asha only has 1 move. Wait, why are we outputting an array? What are we outputting? So for each, we want to output for each indice? For each, like, turn, I guess? I'm kind of confused. Okay, let's see. Prefix of length 1, answer is 3. Prefix of length 2. Masha only has 1 move. So it's 12. How do you get 12? You do, I guess, IJ 13 divided by 2. 6 times 2 is 12. Okay. And then 3 possible moves. It's 3 and 10. She chooses 3 and 10. The final number is 22. How exactly did you get 22? Three and 11. Final number is 24. So 3 plus 11 is 14, divided by 2 is 7, times 2 is 14. Oh, okay. Okay. So we get 11 by this. 10. We remove these, we add 12. What? For a prefix of length 1, the answer is 3. Yeah, 3. If it's just one number, we can't do any operations on it. And the game ends, right? Oh, one person aims to minimize, right? The first person is Masha. Masha aims to maximize. Olia aims to minimize. So, first turn, Masha can't do shit. So Olia aims to minimize. Well, it's 1, so here's the answer. And then, okay, Masha aims to maximize. It's 12 and 11. Twelve plus 11 is 23, divided by 2 is floored is 11, times 2 is 22. So how, what? Oh, for a prefix of length 2. So they're saying we only have these 2, which means it's 12. Okay, that makes sense because then it's length 1, right? For prefix of length 3, Masha has 3 possible moves. Masha To play optimally, we'll do 3 and 11. And then Alia's forced to pick these. Wait, that's just 2 possible moves. She chooses 3 and 10. She'll have 12 and 11. 23. Okay. Yeah, then Alia will operate and get 22. Okay, I see how that's done. Then, if she picks 3 and 11, 14, 7, 14, you have 14, 10, 24. Okay, I see how that's done. 10 and 11, 21. What about 2? 10 times 2 is 20. And then 20 and 3. 23 divided by 2. 11 times 2 is 22. Okay, well, I get it. I think. So, our output should be for I in range n. Okay, let's think. We always want to combine either 2 evens or 2 odds, because then we will lose a number for the floor operation, right? Let me see. In the second test case, if we only get these 2, if we only get this, it's just 6. When we get these 2, you just do the operation. If we get these 3, then you want to pair the odds. 10, and then 16 divided by 2 times 2. And then if we got these, we would do this. We'd simply just do the sum. Sum of these is sum of these, which is 18. If we had these, then we would do I have a theory. What's the sum of all of this? 10, 20, 27 minus 1. Okay. So the last number is going to be the sum of everything minus whether there's an even number of odds or an odd number of odds. Right? I think, maybe. Let's take a look at this. 20, 30, 40... Okay, wait. 20, 40, 51. And then there's 1 odd, 2 odd, 3 odd, 4 odd, 5 odds. So minus 1. Okay. That's an interesting pattern. For this one, there's 2 odds. This is 11, 20, 24. Two odds, so nothing. Okay. I think this is a pattern. So basically what we do is we just sum everything. We count how many odds there are. If there's an odd number of odds, we subtract 1. Okay. I need to stop doing this double equals for assignment. Curve sum plus equals. Okay, I don't. For I in A, curve sum plus equals I, if I mod 2, odd count plus equals 1, if odd count mod 2 to print dot append curve sum minus 1, else print dot append curve sum. Okay, wait, I need to double check this. So 7, this odd count is 1. If odd count mod 2, skip the first time, right? We should skip the first time for I in range 1, for I in range n, if I equals 0, and I is not equal to 0. Of A, I. Append 7, 20. 20 plus 11 is 31. Minus 1, 30. Okay. Then this is 20. 40. Wait. It's not as simple as just adding everything. If you actually want to do curve sum minus 1. So it's 2. It's like this. And in here, curve sum like this. I think. Let's see. So 7, 20. 20 plus 11. Since it's odd, we minus 1. 30. 30 plus 19. It's even. Again, so don't minus 1. Oh, fuck. 30. 30 plus 19 is 48. But the sum of all this is 50. It's two odds. Okay, this tells me something new. It's the number of odd pairs. So it's not just this, it's sum. For each odd pair, we subtract 1. So it actually is this, except we simply just check this. If I does not equal to 0, we do sum minus odd count divided by 2. Sealed. Because it's seven. We're just taking 7. 13. Just taking 20. Odd count is 2 divided by 2 is 1. So in theory we should subtract 1 plus 1. If there's 0 odd, then we'd just be adding 1, which is no good. And yeah, I'm so confused. And odd count is greater than 0. So at least one. If there's 1 odd, then we don't need this check anymore. If there's sum 7, there's 1 odd, so we should do 1 divided by 2 seal is 1, so 7 minus 1 plus 1. And then, okay, so if we had even, so we had 6, then we just spent 6. If we had 6, 8, then it would be 14, right? And then if we get 6, 8, 3, we would get 14. 17, 16. Mm. Okay. Slightly off. So when there's 4 odds, her sum is 50. 4 odds. Clearly want to minus 2. Three odds we want to minus 1. 4 odds we might want to minus 2. 5 odds we minus 0? No, 5 odds we minus 1. 4 is minus 2. 2 is nothing. Wait, what? 2 odds minus 0. Okay, 2 is 0. 3 is 1. 4 is 2. What about 5? 5 is 1. What about 6? Let's add another 1 here. This isn't right. There's something very not right about this. Also, let's think about that 6-8-3 scenario. What is the best move for this? Always do this, get 14. $16. It's always just 16, yeah. Okay. But then this is 7. Some. It's 1 odd, which is 1. What was 6 odd? And so with 1s, 1, 2, 3, 4, 5. Just 1, it's 1. So 1, it's 1. But it's still minus 1. 1, 3. I'm thinking about this wrong. Odd plus odd is even. It really just depends if curve sum is even or odd, not the odd count. Right? This is even. So I can just sum them. This is odd, so I have to subtract 1. This is even, but we do 2 operations, so I have to subtract. Well, it's like even, odd, so -1. And that would be another odd operation, so -2. And then this would be even, even, this, and then -1. So 6 would be group, group, group. And 6 would be 0. Right? It'd be group. Wait, group, group, group. So it's 3 evens, and evens can just sum. So 6 is -0. What's 4 -2? This group, group. This is 30, 20. If we do 20 and 30, 50 divided by 2 is 25. Which is less than 30. Okay. How exactly do we get 30 here? 7 and 20 are pretty straightforward. Oh, also for 30, we only get availability to these 3. 7, 13, 11. Which I don't think it matters. This is 20. Then, yeah, and then 19. We need to make 48. Alright. 30. Is it just greedy? You just go down the line and check if the sum is even or odd. If it's odd, you -1. take a look at this. All of these are even, except for the first number, right? So, okay. Is it our current answer plus our AI? If it's odd, we subtract 1. We get 49 or 48. But then 48 plus 1 is 49. So it should get 48 again, which is not right. So, is it this is 20, so we can just keep this as 31. So we need a minus 1, 30. And then there's 19, so we get 49. Minus 1 is 48. And plus 1 is... Okay, so how exactly do we get 50? We could do 20, 30. 50. Wait, am I tripping? When I got here, I did... Okay, I have 4. 7, 13, 11, 19. Just did bang bang, 20, 30. This will give you 50. Why is it 48? That's because one guy's greedily minimizing, that's right. So the other guy wouldn't do this. They would pick anything else. God, this makes it hard. So, the first guy will always pick 2 odds. The second guy will go. Alright, so let's see. 7, 13, 11, 19, 1. First guy. Second guy. This causes a minus 1. And this becomes 30. First guy. Second guy. 50. I see, I understand. So it depends on the number of odds. Evens don't really matter. Evens will just naturally come at the end. so it really just depends on the number of odds. If it's one odd, it's 0. It's minus 0. Two odds is minus 0. Three odds is minus 1. Four odds, it's minus 1. No, four odds is minus 2. Five odds, it's minus 1. Six odds, it's say I do this, he does this, causes minus 1. I do this, he does this. Well, this would be even. 8. What if I do it's minus 2. Seven's minus 3. Fifteen would be I do, he does, I do, he does. Then I do. It is minus 2 again. 9. I do, he does. Minus 1. 9 is minus 3 again. 0, 0, 1, 2, 1, 2, 3, 2, 3. Is it 3, 4, 3? The 10 would be 4. 11 would be 3. It's okay, so it's 0, 0, 1, 2, 1, 2, 3. 2, 3, 4, 3, etc., etc. 4, 3, 4. Depending on the odd count. I need a formula for this. So, we need to define a 2 subtract. And we need to calculate it somehow. How do I make this pattern? Something like this. Okay, so if n is equal to 0, return 0. N is equal to 1, return 0. Otherwise, return where is it? So at 3, it should be 1. 6, 2, 9, 3, 12, 4. So the start of the cycle so if in mod 3 in mod 3 to subtract current group is in mod 3 in 3, and then the position is in mod 3. So our return should be group plus 1. Okay, wait. If 0 group 1 position is equal to 1, this is it, right? If it's 0, in group 0, position 0, we're not position 1, so we can return 0. If it's 1, we're in group 0, position 1, so we would return group 0 plus 1. That's not right. Is it? Oh, yeah, that's not right. 0, 0, 1, 2 should print 0. 3 should print 1, 4 should print 2, 5 should print 1, 6 should print 2, or should, yeah, 7 should print 3, 8 should print 2, 9 should print 3. Okay, so we just need to add a special case. For oh my gosh. This is wrong. What case? First case. 6, 8, 16, 18, 22, 26. Oh, I think I'm out of memory. Six, 8, 16, 18, 22, 26. 14. Nah. Okay, so first case, just 6. 6 makes sense. Oh wait, I fucked up. This is expected. This is the case, right? 6, 3, 7, 2, 5, 4. So first case it's 6, that's correct. If we have 6, 3, we get 9. Divided by 2 is 8. How do we get... Oh, expected is 8. How do we get 9 here? Sum is 9. We have 1 odd. Which is a minus 0. But this is a minus 1 every time we make... Fuck. I'm still thinking about this wrong. Odd count. If there's 1 odd... Is that really this? This fixes all the second numbers, but ruins the first numbers. So what we need to do is simply add a check if I equals 1. If I equals 0, to print dot append cur sum continue. Bang. We got it. Wow. What a war we went through today. Oh, I do believe this question was it harder than graphs? Was it harder than the snowflake one? We have to find the pattern. Finding this on its own wasn't too bad. Figuring out the pattern was bad. This question was hard. Yeah, I don't know. I would say the graph question was easier than this one, at least logically. I would like to see if I came back to this, would I be able to do it again? This one, I think I would be able to do again, just because my initial intuition was actually correct for this. I just didn't dive deep enough, I want to say. But okay, let's call it here. This has been a longer video, an hour 40, 48, an hour 50 basically. If y'all enjoyed this video, be sure to like and subscribe. I'll see you guys next time. Bye.